All right, hello. It's definitely midterm day because like no one's here. So we'll blast through this and I guess discuss midterm stuff and I guess lab 3 stuff because some interesting things happened. But let's go through this quick. So locks implementation. Oh God, there's more questions. When there are 2 forks, all right, people are still asking midterm questions even though it's definitely a lecture, so we'll get to them if we have time, which we probably will. So locks implementation. So we were talking about locks. We tried to implement it. It didn't quite work because we still had a data race when we implemented a lock. Well, there's some like baseline things you need in hardware to actually implement locks. So very basic requirements are like loads and stores are atomic. So you can't, they either happen or they don't. And instructions execute in order, and then that's all you need to implement locking. There's 2 main algorithms if you don't have any special hardware support. Peterson's algorithm and Lampard's bakery algorithm, which kind of mimics going into a bakery and picking a number and then round robining. We have kind of an idea of that before. Every thread has its own storage, then they all kind of vote. But problem is they don't really scale that well. You need more space depending on how many threads you have, and it's pretty awful. So you actually want some hardware support. And we got this yesterday, some magical instructions. Someone already knew of this, but this is okay if it's your first time seeing it. There is a magical atomic hardware instruction called compare and swap. And it takes a pointer to some value you want to change. The second argument here is old, so it's what you expect the value to be if it's to change it, and then new is what you want to change it to. And what will happen atomically is it will try and change the value pointed to, and it will return what the original value is. And it does this all atomically. So if our arguments here are L, what I want to change, and then 0 and 1, it will return 0 only if it atomically changed the value from a 0 to a 1. Otherwise, it's going to return 1 to say it didn't actually change the value. So now if we have this function and we go and try our lock again, because the whole compare and swap is atomic, this is our entire implementation. So before, when we had the while loop, we checked, oh, is it 1? We just keep on looping until it hits 0, and then we would break out of the loop and then change it to a 1. Here, we can just replace that all with a compare and swap. So it will go through this loop as long as that value is 1, because compare and swap would return the value that it's pointed to, so it would return 1 as long as that value is 1. And then if it returns 0, it means it changed the value from a 0 to a 1, and it did it atomically, so no one else was able to interrupt it in the middle of that. So if it returns 0, you changed it from a 0 to a 1, and only you changed it. So after the while loop, you break out of it, it's a 1. Yep.
Is this a real function?
Yeah, so this is not only is it a real function you can call, it's a real hardware instruction. So there's a CPU instruction called compare and swap. I think we see it later. Sometimes it's called comp exchange or compare and exchange. They shorten it because, of course, why not? But every hardware has something that's essentially like this. So it is a built-in. You can use it as a function if you want, but it's actually a hardware instruction. So this is actually a good implementation of a lock. This is a valid implementation, although it kind of sucks. Any ideas as why this kind of sucks, even though it works? Yep.
Cache efficiency is very bad because you read it like it trying to set it like it's not cache efficient.
The caches shouldn't really matter because it's just one value we're changing, so it has to be somewhere. So our main problem here is like that while loop, that especially if it's like a single core on that machine, it'll just try it over and over again and essentially waste a bunch of times when it knows it can't actually change the value, or so it will actually consume cycles, consume instructions. It'll just like compare, go back, compare, go back, compare, go back, not really doing any useful work. So this does work, but it has, a bit of a problem where it might waste some time. So, but that lock is a valid lock in some cases if you know that value might change quick, or the lock is protecting something that happens very, very quickly. Maybe you don't want to do anything special. Maybe you just want to try again, and that's the best thing. So that is what people typically refer to as a spin lock. And they call it a spin lock because it just spins. It just tries over and over again. So yeah, compare and swap is that atomic hardware instruction. So here's that name on x86. This was when I tried to pronounce exchange. It says compare and exchange. Depending on who made the hardware, they might call it something different, but it essentially does the same thing. So yeah, like I was saying, if you have one core on your CPU and you can't get the lock, you may as well not try again because you're the only thread running, so nothing's going to change it for you. On a multi-processor machine with lots of cores, well, maybe you want to try again. Again, like I said, if it's protecting something very small, if you try maybe a few times, you might get it the next time. So we kind of did this. You implement this, or hopefully have started thinking about it, at least in lab 3. Well, you could just add a yield if you know you can't do anything useful. So I have that same while loop, but instead of just trying over and over again, if I don't get the lock, I will just yield. And it'll say, yeah, run something else. Hopefully it unlocks it because I didn't get it. But that has its own problems. One's like something called a thundering herd, where if you have multiple threads all waiting on the same lock, they'll all yield, and then it'll kind of just stack up, and they'll be like, 10, maybe hundreds of threads waiting on that lock, all in the queue, all being requeued over and over again, when realistically, if 100 threads are trying for the same lock, you already know ahead of time that only one's going to be able to grab it anyways, so why am I bothering just cycling through like 999 of them that won't get it in the next round? And also with that, everyone's just running this loop over and over again and going through the round robin, assuming we're doing round robin. And you can't really reason about who gets the lock next. It's just whoever happens to get it next. So if you want to be fair and be able to reason about it, you need some type of ordering, and this wouldn't have it. So we can implement a queue. So you can add a wait queue for a lock. So it's just like your ready queue, or if you have a blocking queue or whatever. So I could just say, hey, for this lock, I will implement a queue with it for everyone that's waiting for it. So here I'll do compare and swap. And then if I don't get the lock, I go into the while loop. So instead of just yielding, I will put myself on a queue and then use something called thread sleep, which you didn't have to implement, but it's not too hard to reason about. Thread sleep will put this thread to sleep and put it in a special block queue where another thread has to explicitly wake it up and tell it, okay, you can go in the ready queue again. So you essentially block yourself, you put yourself in a waiting queue that says, hey, don't execute me, I'm actually waiting for something. Then you put yourself to sleep. And the idea here is that whatever thread has the lock eventually will call unlock. It would set it to 0 to indicate that that lock is available again. And then it would check that, hey, if there's any threads in the wait queue, I'll just wake up one thread and whatever's at the head of the list, so you can reason about it, so it's first in, first out order. So there's 2 issues with this. One is something called a lost wake up, and 2 is creatively name the wrong thread gets a lock. So anyone want to point out to me how bad situations could actually happen with this code? Or guess what a lost wake up is? Yep.
Is it when you get preempted between entering the while and adding yourself to the wait queue if you haven't added yourself yet, and then the other one unlocks and you're not in the wait queue?
Yep. Were you going to say the same thing? Yeah, so that is correct. So what could happen is, let's assume we have a thread running that's calling lock that doesn't get the lock, and another thread has the lock. Well, what might happen is I check the condition, I don't have the lock, so I go into the while loop, and I want to add myself to the queue. That's my next thing I'm going to do. but I get context switched, right? Essentially, I get yielded without, consenting to it. And it switches to another thread. And it could switch to the thread that's going to call unlock. Oh, yep. Oh, so get a lock means one thread made it through this lock call. So it changed the value from a 0 to a 1, and it's the sole owner of that lock. Yeah, so in unlock, if you have the lock, and remember when we reasoned about before, if only one thread should pass lock, and it would set it from a 0 to a 1, and then in unlocked, it means, hey, I'm done with it, and it just has to set to 0. Yeah. Yeah, so if it's locked right now, the global state, somewhere that value of the L is equal to 1 because another thread would have acquired the lock. It's doing some critical section. It's doing something. So yeah, so I would have, in a thread that is trying to acquire the lock, so it calls lock, it would go into the while loop. It would say, hey, it's already locked. I cannot get it. So it would go here, and the next thing it wants to do is add itself to the queue, but I could get preempted right before I add myself to the queue. And now this is the thread that would have the lock. So this is the thread that set L equal to 1. And if it's going to unlock it, well, it would set it to 0 here because it's the only one with the lock. There's no data races because if it acquires the lock, it's the only one with it. So I can just set the lock to 0, and now it's available for other threads again. So it might continue executing. If it continues executing, then it would check, hey, is there any threads in the wait queue? And right now, there is not, because the other one hasn't added itself yet. And then it wouldn't go into here. It wouldn't wake up anything because there's nothing there, and then just exit. Exit, return from this function, carry on, do whatever it's going to do. Now, when we come back to this thread, well, it is now unlocked, so the value of the lock is 0. Now it would add itself to the wait queue, and then put itself to sleep, and now nothing. So it's just going to sit there. Nothing is ever going to wake it back up again. Unless another thread, goes and acquires the lock and then unlocks it, but, it might have missed a single wake up. So does that make sense to everyone? Bad things happen. So the other one is the wrong thread gets the lock. And the idea of that is you're supposed to be fair. So if you're waiting for a lock and you're the first one waiting for it, you should be the first one to get it. So there might be a scenario where, let's say, we have 3 threads. So we have, let's see, 3 threads, T1, and let's say T1 is already in wait queue. So it tried to get the lock. It couldn't get it because thread 2 has the lock. So this is our scenario. So T2 has the lock. It's going to unlock it at some point, and T1 is first in line. It tried to get the lock. It executed. It put itself in the wait queue and put itself to sleep. So there might be a scenario where T2 has the lock. It calls unlock. So right now, the value of the lock is equal to 1. And so T2 calls unlock. It would change that 1 to a 0. And at that point, it might get preempted. So it might get preempted, switch to another thread. Let's call this tricky thread thread 3. So it switches to thread 3, and thread 3 calls lock. So if thread 3 calls lock, well, it would check the condition. Right now, the lock is unlocked, so it would change it from a 0 to a 1 and essentially get the lock and pass lock, and now thread 3 just kind of swooped in there. Thread 1 was patiently waiting. Thread 3 just came in, swooped it up, and now it has the lock instead of what we would imagine. Thread 1 was nicely waiting. So does that make sense to everyone? Cool. So here is the lost wake up example. So what we just demonstrated, where thread 1, we have 2 threads, thread 1 and thread 2. Thread 2 has the lock. So if thread 1 gets into the loop and swaps before it adds itself to the wait queue, then T2 unlocks. It would check if there's anything in the queue. There's not, so it wouldn't wake up anything else. And then that thread just puts itself to sleep, and now no one, potentially nothing will ever wake it up again. And then this was the wrong thread getting the lock. There's already something in the queue, but the thread 2 that holds the lock unlocks it. And this one, I swapped thread 1 and thread 3 from what I was talking about, but idea is still the same. Some new thread came in, swooped up the lock. Yep.
Since it's a queue, how could T1 steal the lock from T3?
Sorry, what do you mean? So it's in a queue, but if it got preempted, here, go back. So if whatever was executing got preempted before it checked the queue, then it doesn't even look at the queue, and the other thread would go acquire the lock before it checked the thread that was unlocking actually checked the queue. So it would just grab the lock, and then it would wake up that thread that was patiently waiting for the lock, and then it would just try again in the while loop, and it would be like, oh crap, well it's still locked, so I put myself to sleep again. But so essentially, nothing bad will happen. It'll just be in a different order than you expect because one thread was waiting around a long time. Okay, and here's how you fix it. So the fix of this, it looks really, really ugly, but it's actually not that bad if you translate some things. So basically, this uses a spin lock internally, and the idea behind that is these things aren't very big. They don't take very long. So you can use a spin lock, which is a perfectly valid lock, even though it wastes some time. So you kind of need it. So if you see this, there's going to be a spin lock called guard that I only use within these functions. So if you see this is essentially a guard mutex that I am locking. And if you ever set the guard to 0, it means I'm unlocking that spin lock. So if you translate it, it's a little bit easier to read, but this is what the code would look like. But of course, you could refactor it. So in the lock, I would acquire the guard lock, and both these functions, the first thing they do is acquire the guard lock, so I can't get preempted in between them. So I have mutual exclusion, no data races, only one thread has this guard lock at a single time. So I have the guard if it passes through this while loop, so whatever I do is fine. In fact, it makes I don't need compare and swap for the actual lock value because I don't have any data races anymore because there's mutual exclusion. There's only one thread executing it. So makes it a bit easier to read. So I check if the lock is unlocked, well, I change the value from a 0 to a 1. And then I can unlock the guard because I'm done with this function. I just immediately acquired the lock. I don't have to do anything special. And then in the other case where I don't acquire the lock, well, I would add myself to the queue. This is just however you implement the queue. And then I would unlock the guard and then finally put myself to sleep. And then whenever you call wake up, it would just resume like it just returned from sleep, so the thread would just wake up here. And the idea is we would transfer the lock there because we're only going to wake it up from the unlock function, and we'll see that. So in unlock, you have a call to lock the guard lock. So after that, you have mutual exclusion. Then it would check if the queue is empty. If the queue is empty, well, then I just set the lock to 0 to indicate I unlocked it. So I change it from 1 to 0, and that's it. Otherwise, I don't set the value to 0. I just keep it as 1 because I'm essentially I'm only going to wake up one thread, and I know one thread was waiting on that lock. So I'll just keep it locked, and I'll say, OK, it's your issue now. You deal with it. So I would wake it up, and take it out of the queue, whatever was first in the queue, and then I can unlock it. So does this kind of make sense? Yep.
Is the idea that we're taking the previous code and making it so that only one thread can run certain parts of it?
Yeah. Yeah, so the idea is I'm taking the previous code and fixing the lost wake up thing and the wrong thread getting the lock. So I prevented both of those this time because of this guard lock. Only one thread can do this at a time. So if I'm patiently waiting, nothing can swoop in because the problem was with the wrong thread getting the lock, when the thread with the lock just changed the value, then it context switched over to another one that was calling lock. But now that can't happen anymore because if the thread that is unlocking acquires the guard and then changes the lock to a 0, well, another thread can't call lock because it would have to acquire the guard, and this thread has the guard. So it can't come in and kind of like swoop it, right? So is there any problems with this code? Because there's still a subtle data race here. So this isn't quite correct, but it's actually not too bad. Yeah?
Should we have two concurrent swaps in here?
Nope.
No idea.
No idea? Okay, so if I unlock the guard here, I could context switch, right? Another thread could call unlock or something like that. So there's a subtle little bug here, or a subtle data race here that you could actually detect, so it's not that bad. So what could happen is, say one thread has the lock already and another thread is trying to acquire it. So it would grab the guard, try, the current value is 0, so it would come, or sorry, the current value is 1. So it would come into here, add itself to the queue, and then unlock the guard. So if it context switches after unlocking the guard and before calling sleep, well, it's currently not asleep, so it's not blocked, it's still technically active. And then the other thread with the lock can actually call unlock now because the guard is unlocked, so it could pass through this while loop. And it would check, well, the queue's not empty because it added itself to the queue at least. So it would get here and then try and wake up that queue or that thread, but that thread is not currently asleep. So yeah, so it adds itself to the queue, it knows it needs to wake something up, but that thread might not actually be asleep yet. But this isn't that bad of a problem because you don't have a data race involving the queue, so you know it's about to go to sleep. So I can just try this a few times, but you have to be careful because it's like almost right, and you might not switch right before the sleep. So it's like a subtle data race, but it's not too bad and you can actually detect it. So any questions about that? We are steaming through this. Cool. All right, so that was basically that explanation that there's still kind of a data race where you get interrupted right before the thread sleep, and then another thread would do the unlock and then try and wake you up, but you haven't fallen asleep yet. So, but again, you know it's about to sleep, so you could just try it over and over again until it actually goes to sleep. So yeah, very important, especially for even in lab 3 where you essentially have very, very, very well-defined concurrency, so you have to yield, otherwise it won't be taken away from you. You still might need to worry about this in part of your lab 3 in very special circumstances. And again, it's kind of tricky. A data race is when two concurrent actions access the same variable and at least one of them is a write. And you have to be very, very, very careful about this. But that also means that you can have as many readers as you want, and maybe you want to implement something like that. So you don't need a mutex or any protection as long as everyone's reading. So as long as nothing's writing, you can go ahead, have as many threads accessing it as you want. So you might want to have a lock that allows a lot of readers and only one writer, so there isn't any data races. And that is what a read-write lock is. Actually, this is a good segue. So this in lab 3, remember I was kind of talking crap about like, hey, no one can cause my thing to seg fault. Yeah, that was a bad idea. Someone caused it to seg fault. And as a reward, I will tell you what happened because it will probably happen to you because it was in my solution and it was in the TA solution. So both solutions had this problem, and I'm going to imagine yours would too. So here we go, you broke it. So this is likely what happened. Well, this is what happened in mine, and I can almost guarantee you have the exact same issue. So in what join, when you implement that, you'll have all kinds of checks for errors to make sure that it's actually running, blah, 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 all that stuff. So in my code, at least, when I was keeping track of everything, I essentially had a pointer that was like a dynamically allocated array. So I had it, I set it, it was, whatever, and then I had to put this thread to sleep because it was waiting on something else. So I would swap context away from it, and then eventually I would swap context back to it whenever that thread actually wakes up. And between those, I dynamically changed that pointer because I had to resize the array. So now the value of this pointer variable, this one, was the old value, still the old value, even though I changed it because it context switched back here and it was still the old value. So whenever I tried to access it, only if I resized something between when I swapped away from it and when I swapped back, then I accessed it and I seg faulted. Yeah.
Does that mean the resizable pointer was a global variable?
Yeah. Yeah, so in this case, I had a global variable that was just the whole, like basically a global variable that pointed at my dynamically allocated thing, and it moved between these. So, yeah.
What do you mean by resize the array?
So resizable point, so it just means I was pointing at some dynamically allocated memory, and I was using realloc array. So sometimes realloc array, when you say, hey, I want more memory, it will actually move everything because there's not enough room to place it where it is. So in some cases, for me, it would move everything. So if it needed to move it, that value changed, and that's a data race because I was essentially changing that global variable, and I had two concurrent accesses. So one thread was changing it, while another thread, was reading it. So it read it here, and a write happened in between those, and I shot myself in the foot because C is so fun, right? Everyone loves C. Yep.
Sorry, what is the resizable pointer for? I thought we were supposed to use the tail view.
Yeah, so in mine, I mean, you're going to have it too, where you have the information that keeps track of all the threads, and you don't know how many you're going to have, so it's a dynamically allocated array. So I just had that, and I changed it. I changed it between the two calls, right? So this thread was joining on something, it went to sleep, and then while everything was executing, I had to make it bigger, and then when I came back, it was like, okay, yeah, I know where it is, and it was the old value, which is now no longer valid. Yeah.
Is it using linked list to address this problem? If you use linked list?
Sorry?
If you use like linked list instead of like the resizable array?
So if you use a linked list, that's okay as long as you don't, it's the same data race thing, right? If you saved some value that could change by the time you come back, you'll encounter this problem.
So why do you change the pointer?
Because I had to make it bigger.
Because linked list you can link it to the end, right?
Yeah, but it depends. Like if you're changing yeah, you could, if I save the element of the linked list, by the time I come back, that element could no longer exist. It depends on your implementation. Oh God, yeah.
Isn't it because, like, when you do realloc, it has to be stored contiguously, so it copies everything? But if you
Yeah.
use a linked div list, can't you keep, can't it still be like kind of fragmented?
Yeah, it's fragmented, so like you can go on to the next one.
Yeah, it depends, but like if you were keeping track of some other element and by the time you came back it doesn't exist anymore, then you're gonna have a seg fault. So it depends on your implementation, yeah.
What if you use like a pointer to a pointer instead? So like if you come back and you change what, like every time you reallocate, you would reallocate what the pointer points to. So that when you come back to here,
So that still doesn't help if I just like save the value of that pointer, right? There's an easy fix to this. What's my easy fix?
don't use dynamic elevation.
That's never the right solution. Yeah, I saved it to a local variable, so I should just read it again. So, yeah, that was my fix. So you just take this and you go yee and just set it again, right? So you get the most up-to-date one by the time you get back, and that's the fix. Yeah.
Are we provided with that test cases, like, always already like the existing ones? Just like,
Nope. Well, there's no one test case. This really depends on your solution to break. Yeah.
So the like general problem with this is that you're storing something to a local variable, swapping context that could then change what you had read,
Yep.
and then like relying on what it was before.
Yep. Yeah. The basic crux, it's a data race. So I read a value, and by the time I use it again, it got modified, and I read the old one. Yeah.
are more test cases going to be added for the lab 3?
Oh, yeah. You guys added lots.
So, before the final submission on Monday, will we get like a final grade like how we had in lab 2 where we knew that we were getting 100 or whatever? Something like that for lab 3, or are they going to be like hidden test cases that we don't know about?
There's going to be some hidden test cases because some are really big and pretty good. So yeah, there'll probably be some. And like some of this bug only comes up depending on like where you resize. So I resized after like 8 or something. It just happened that one of the test cases did this with thread 8 when I had to resize it. So like you're not going to be safe if you just make a huge array because it's really easy to tweak how many threads you make, and it's a lot harder to allocate way more memory. Yeah.
So have the final test cases, like if you just get pull again, will they be available?
No, I have to like manually convert them.
So we don't know if the changes that we make for the additions for 1.1 will work or not until the new test cases come?
Yeah, so there'll probably be hidden test cases that you don't know. I might try and add some more test cases before it's due, just for more sanity check. But yeah, the point of that is you made your own test case too, and hopefully you got an answer from the solution, so you kind of know if you're on the right track or not. Yeah.
Do you know how many more test cases will be added in addition to what we already have?
Yeah, I have to make it, so I don't know. Yeah.
Is there anything stopping us from crowdsourcing everyone's test cases and solutions? Like expected output?
Yeah, sure. If someone wants to volunteer for that, just do it. It saves me a lot of time. If so,
Like we actually can, like if we created like a thing where people could put their test cases so that we could all test it that way? Because we would, like that would definitely make it a lot easier to get a good mark.
yeah, but I guess I gave you the solution, so you know what it should be. We can crowdsource in a. Yeah, we can all crowdsource, and I will oversee it. So I can convert some test cases. Sure, I'll just add test cases, and people can tell me to add their test cases or not, and I'll add it for everyone. So you don't have to form little groups and have like a group that does good and a group that does crappy. So yeah, I guess I'll add more test cases, but yeah, looking at some of you are not very good at writing test cases or converting them, so I will do it. So yeah, I will add more test cases, but unfortunately, I don't have an infinite amount of time. Okay, any other questions or midterm related or anything like that? Because it's, I guess, later tonight, which kind of sucks. Yeah. Do you need a calculator? No.
Can we bring a calculator?
Type 3 or whatever, basic dumb calculators, sure. If a calculator makes you feel better, go for it. It'll be like 2 to the power of something, and I think on it, it's like the last one where you can leave in powers of 2 if you want. So the hardest thing you have to do is add or subtract, and like up to like 30s. So if you can't do that faster than a calculator, then sure, it makes you feel better. But yeah, it's generally, if you ask that question and a prof doesn't care, it means it's not going to help you. All right, any other questions or concerns or anything? Other than it's later tonight. Yeah, but that seg fault will definitely be in your code even if you allocate a huge array, eventually it's going to pop up, and I guarantee you did not think of it. So yeah, depending on your implementation. And make sure you read the new what join thing, because the rule that was implied that I didn't spell out is that you can only wait on an active thread, so then you can't have the situation where 1 waits on 2 and 2 waits on 1, or you also can't create any cycles and you don't have to detect it or anything like that. So, all right, if there's no questions, I guess for the record, we can clean up. So yeah, read-write lock. Whew, going back. So if you want however many writers, or to allow however many readers you want and only 1 writer at a time, well, there's a special read-write lock, and the idea of it is kind of the same idea. So I will reuse the mutex. So now I'll just call them the mutexes or spin locks. I'll just call them locks because it doesn't really matter which one they are. So I'll use a guard lock that I only use within all of these 4 functions, and then a lock that I use to represent the write lock, like the actual lock. And then I also have a variable to keep track of how many threads are currently reading the value. So in the terms of write lock, I only want 1 thread in there at a time. So my write lock and my write unlock just simply lock and unlock that mutex or whatever it happens to be, that lock variable. Now, in the read lock, I would try and grab the guard, so I'm the only one modifying this number of readers, so I don't have any data races. So this is essentially like that plus counter thing. So I don't want any data races with it because I'm keeping track of the number of readers. So in here, I increment the number of readers, and then I check. Well, if I incremented the number of readers from a 0 to a 1, that means I'm the first reader, and I have to acquire this underlying lock, and then I know I now have the lock, and we're the only ones with it at this point. And then I can unlock the guard, and then other threads can come in and call read lock or read unlock. So if another thread comes in and calls read lock again, well, I can have 2 readers, that's okay, that's not a data race because they're both just reading. So it would acquire the guard, increment the number of readers from like 1 to 2, and it doesn't have to acquire the lock because a reader already got it. So it can unlock, and this could happen as many times as you want. So you could have 10 readers, 1,000 readers, 10,000 readers, whatever you want. Then eventually, some of them are going to call read unlock. So it would, again, acquire that guard, subtract the number of readers because it's trying to unlock it, and only the last reader would unlock that mutex. So if this is like, say we had 2 readers, if this one decremented it from a 2 to a 1, it wouldn't have to unlock that underlying mutex because there's still a reader trying to read it. So I don't do anything, I just unlock the guard. And the only thing happens is when I decrement the number of readers from 1 to 0, which means I was the only reader left, I can unlock the lock because now nothing is nothing is reading it anymore, and now a write lock could come in. Writer could acquire it, be the only one. So with this implementation, I could have either a single writer or as many readers as I want, and not both. So this will give you, right, if writes are very, very seldom, you might want to do something like this, because if you just did a lock, well, anything reading or writing would have to be protected, and only one thread could do it, which would be really, really slow. But if writes are really infrequent, you would do this, and then you can have as much parallelism as you want, because they would all be reading, and they could, lots of them could read at the same time. So any questions about that? Cool. All right, that's pretty much it. So the whole crux of this is you need some critical sections to protect against data races, and you also need to reason about them, because even in Lab 3, you will still get data races, because now we have that dreaded thing called concurrency, even if in Lab 3 it's actually not too bad. So you need, like, mutexes or spin locks are like the most straightforward locks. They just only allow one thing to pass lock at a time, and that's it. So spin locks just try over and over again. Mutexes usually are a bit more involved and will put themselves to sleep if they don't acquire the lock. But to implement locks, you typically need some hardware support, so that's that compare and swap instruction. You would need some curl support for wake-up notifications. So if you really wanted to in Lab 3, if you were really bored, you could implement a sleep and a wake-up if you really wanted to. So that's up to you, but that's not there. I intentionally took that out just to save you a bit of time. And then, yeah, lastly, there's special types of locks. So if we know we have lots of readers, we should use a read-write lock, because it's not a data race if everything's reading. So just remember, pulling for you. We're all in this together.